Hey everyone, Mr. Graham here. Today I want to show you a little bit of, I want to talk a little bit about the kinematic equations. I've listed them up here, the three kinematic equations. They are on your formula sheet. Obviously you need to use them in order to solve kinematics problems, both in the x direction, the y direction, in both dimensions if we're doing projectiles. And as we'll see later in the year, we actually do physics in the z direction as well. So we'll add an extra dimension on, not quite yet though, so don't worry about that too much. Right now, I just want to focus on one-dimensional motion. That's why I got the x's here. So I got the x subscripts, and I got displacements as x minus x naught, final minus initial position. Realize that if you're dealing with vertical direction motion, like the free fall motion, we replace the x's with y's. If we're dealing with the z direction, we replace the x's with z's. That's it. Just so you know, when I do kinematics problems, if I know what dimension I'm dealing with, then I just drop the subscripts and I just assume that I'm dealing in the x or the y direction. When I'm doing projectiles, I use the subscripts though, just because the directions are important. It's very important to know whether you're dealing with the x or the y direction because one direction has acceleration and one does not. Okay, now to start our process here, well, what the process is, I want to show you 3 videos. Each one covering how we actually can derive these equations. If you really want to know physics, it's not just a matter of being able to use the equations to solve problems. If you really want to understand physics at a gut level, you got to know where the equations come from. So I'm going to show you one way, one of the many ways, that we can derive these 3 equations. And I'm actually going to use an actual graph of velocity versus time for this object sliding down, rolling down a ramp. And we should know at this point that when an object rolls or slides down a ramp with no friction, we do get uniformly accelerated motion. So it'll look like this. There we go, nice and linear. At the end, that's when it was kind of stopping at the end, but for the uniformly accelerated motion part, this is pretty much linear. And so what I'm gonna do is just kind of superimpose my own coordinate system here, where the vertical represents velocity, the horizontal represents time. This is obviously a velocity versus time graph. All right, let me get this off. Oop. So we did see that the graph looks something like this. Now I'm gonna label some stuff. Notice I let the cart start moving before I hit the collect button because I wanted it to have some initial velocity as recorded by the data. And that initial velocity would be right here. And then after some amount of time t, then the cart will be at some final velocity, which I will just call v. Again, if we're using our subscripts, this would be vx, this would be vx naught, okay? All right, now at this point, we should understand that the slope on a velocity time graph is acceleration. So I'm actually gonna use that definition of acceleration, or that way of determining acceleration from the velocity versus time graph to generate kinematic equation number 1. And how I'm going to do that is just remember from math class the slope-intercept form of the equation for a line, which is y equals mx plus b. In this case, though, our y value just indicates the final value for velocity. The vertical axis represents velocity. Therefore, the y value here from math class turns into final velocity v. The slope, again, on a velocity time graph is acceleration. The x-axis is represented by the time t, so I replace the x with the t, plus the y-intercept. In this case, the y-intercept is just the velocity that the cart started at. So that's going to be v naught. And then I can just reorder. You learned this in math class. The order of addition does not matter. So I can swap those 2 terms, and I get final velocity equals initial velocity plus the acceleration times time. And right there is kinematic equation number 1. Okay? Stay tuned for kinematic equation number 2.